Hi, everyone. Thanks for tuning in. My name is Hayden, and I will be talking about maximizing the Eastern Sierra Nevada snowpack by finding the optimal canopy cover and terrain features for snow accumulation and retention. First off, I want to give some background information about the Sierra Nevada snowpack and forests. Runoff from the Sierras provide water to 60% of California's population and 75% of all the crops and livestock grown in the state. And it's estimated that a third to one half of California's total water supply is from meltwater. So the snowpack is vital to the water supply and acts as an enormous frozen reservoir that provides water throughout the year as it melts. And the major threat to the snowpack is climate change. The rising temperatures will cause 25% of the snowpack to disappear in less than 30 years, and 60% will be gone by the end of the century at our current rate. So the amount of water available to society will be reduced, but climate change will also melt the snow faster and earlier in the year. And that's a problem because we want the snow to melt gradually into summer so that there is enough water for everyone during those dry months. So the question is, how can we help mitigate the effects of climate change? And one way is with silviculture, which is defined as the practice of controlling the growth, composition, and structure of the forest to meet our needs. So we can modify the forest to accumulate more snow and retain it for longer by manipulating the water and energy budget, which the figure on the right is showing. Forests affect the water budget by intercepting snow in the canopy, and it's sublimating, which just means it either evaporates or blows away before it reaches the ground and accumulates. And also, trees can capture solar radiation and re-radiate it to the surrounding area, which can accelerate melting. But at the same time, trees can also provide shade and reduce wind speed, which would decrease melting. So there's a balancing act that makes it difficult to anticipate how fast melting will be. In addition to trees and canopy cover, the physical landscape influences snow accumulation and melting. And the big three topographic features are elevation, aspect, and slope. Aspect is what direction the side of a mountain faces. So just like a compass, 0 degrees is north, 90 is east, 180 south, and 270 is west. Because of Earth's tilt in orbit around the sun, the amount of radiation changes with aspect. And lastly, slope is how steep an area is from 0 degrees flat to 90 degrees vertical. And that will affect how snow settles on the ground due to gravity. So knowing that canopy cover and the terrain affects snow distribution, I want to see how much canopy cover and what terrain features result in the most snow accumulation and the longest melt times. And that's what I base my research questions on. The first two sub-questions are dedicated to finding the optimal canopy cover, which maximizes peak snow water equivalent and melt duration. And the third is finding what elevation, slope, and aspect have the most peak snow water equivalent and melt duration. And I'm using peak snow water equivalent to measure snow accumulation. And that is the amount of liquid water left if the snowpack melts completely when the snowpack was at its biggest in the year. So it's a good metric to use because I care about maximizing the amount of runoff for human use. The study site that I'm looking at is the Owens River Headwaters Wilderness in the Eastern Sierras. It's about 15,000 acres and it's right next to Mono Lake and Mammoth Lakes, if you're familiar with that area. And I chose it because the Owens River provides 1/3 of LA County's water. So this area at the headwaters where the river begins has potential to increase the amount of water flowing through the Owens that ultimately ends up in the homes and businesses of LA residents. I used 3 remotely sensed data sets for my project. I used a snow water equivalent data set, a percent canopy cover data set from the Forest Service, and a digital elevation model from the US Geological Survey. I used a program called QGIS and uploaded these data sets to it and created the slope and aspect variables using the digital elevation model. Then I sampled every pixel, which has about a 90-meter resolution, to get a complete data set where each data point has a percent canopy cover value, elevation, slope, aspect, and daily snow water equivalent values. Now I want to discuss my study design and describe how I answered each sub-question. For the first one, I'm trying to find what amount of canopy cover results in the most peak snow water equivalent. So I divided the data into groups based on low, medium, or high canopy cover. Low is 0 to 25%, medium is 25 to 50, and high is 50 to 75. Then I used an ANOVA, or a one-way analysis of variance, which basically averages the peak snow water equivalent for each group and compares those group means. And the ANOVA will tell me if there is a statistically significant difference between the groups. So if the p-value is under 0.05, it means that the groups differed and that one has more peak snow water equivalent than the others. The ANOVA only tells me if the group averages are different, but not which group specifically differed from each other. And that's what the Games Howell post hoc test does. It tries each combination of groups like low, medium, low, high, medium, high, and so on, and tells me which combos were statistically significant. So at the end of all that, I will know what canopy cover group had the most snow accumulation. And the second sub question has identical methods to the first, the only difference being that I'm using melt duration as the variable instead of peak snow water equivalent. And the third is trying to find what terrain features result in the most peak snow water equivalent melt duration. So I made multiple scatter plots with elevation, slope, and aspect on the x-axis, and peak snow water equivalent and melt duration on the y-axis. Then I calculated the regression line and correlations between these variables, and I can use the graphs to see where peak snow water equivalent melt duration are maximized. And from the R² correlation values, I will know how important each variable is to the snowpack. Moving on to results, I also divided these slides up based on sub-question. And for the first one, the ANOVA test had a p-value that was incredibly small, basically 0, which means that there were differences in snow accumulation between the canopy cover groups. And looking at the raw data, the one in blue, the highest peak snow water equivalent occurred in open areas with 0 canopy cover, and peak snow water equivalent decreased with canopy cover until around the 40% mark, and then started to increase again. And the box plot shows the results of the ANOVA after I divided up the data into groups. The low canopy cover had slightly more peak snow water equivalent than the high canopy cover, but not enough to be statistically significant in the post hoc test. And the medium canopy cover had the least snow water equivalent, almost 15% less than the low canopy cover group. And that one was statistically significantly different from both the low and high cover groups. For the second sub question, the graph on the left shows a strong upward trend, and the p-value from the ANOVA was again practically 0. So there were statistically significant differences in melt duration between groups. And the post hoc test showed every combination of groups was different. And the highest canopy cover group retained the snow the longest, followed by the medium group, and in last place, low, which melted the fastest. And the difference in melt times between that low group and the high one was about a week and a half. The next 3 slides are the results of the third sub question, trying to determine what the optimal terrain features are for snow accumulation and retention. So starting off with elevation, there's a positive correlation between both peak snow water equivalent and melt duration. And the higher that the R² value is, the stronger the association between the two variables are. So elevation is important to melt duration. There's more important to melt duration than it is to peak snow water equivalent. And the important takeaway here is that at higher elevations, there's more snow and it lasts longer than at lower elevations. Next up is aspect. One thing to note is that I changed aspect into northness by taking the cosine. So rather than being from 0 to 360 degrees, the cosine of aspect allows me to see a linear relationship where -1 is south and 1 is directly north. And as you can see from the graphs, melt duration and peak snow water equivalent increased as aspect became more north. And the R² values are pretty high and roughly equal, so northness is an important variable to the snowpack. And the main takeaway here is that north-facing slopes are better at accumulating and keeping snow for longer before it melts. So the last one is slope, and the graphs definitely look a little strange. The R² values for these graphs are 0, or at least basically 0. So slope had a negligible effect on peak snow water equivalent and melt duration. And the way that this is graphed makes the fluctuations look more profound than they actually are, because the scale on the y-axis is not starting at 0. But the variability in peak snow water equivalent and melt duration increased with slope, which you can see with those huge standard deviation bars at higher slopes. So slope didn't really tell me much about snow accumulation or retention, other than at higher slopes, peak snow water equivalent and melt duration are more random and harder to predict. The last content slide I have is implications and synthesizing all of these results. And the goal of my research is to be able to inform forest management by determining what amount of canopy cover is ideal for water resources, and where silviculture would be most effective. So what would the ideal forest look like? Well, we know we want to minimize the amount of medium canopy cover in that 25 to 50% range because it accumulated less snow. And we know that open areas accumulated the most snow, but the high canopy cover areas had the longest melt times. So based on that, I think the ideal forest would look something like the photo on the right. The forest has high canopy cover with pockets of open area in between. And those open areas will accumulate the most snow while the high canopy cover around it will block wind and offer shade from the sun. And this should be a good combination that optimizes both snow accumulation and melt duration. So if the Forest Service decided to replicate this forest structure, the results of my third sub question with the terrain variables could help them determine where to start. And at higher elevations on north facing slopes, they naturally accumulate the most snow and retain it for longer. So thinning the forest in places that fit that description will have the most benefit. All right, that is the end of my presentation. Thank you to the 175 instructors for helping me along the way and keeping me on track. And a big thank you to Marianne Cowherd, who mentored me for the past year and answered all my questions and really helped me every step of the way. And thank you to Dr. Girato, who put me in contact with my mentor, Marianne, and allowed me to use her snow water equivalent data set. And finally, thank you to my roommates, Brian and Evan. Brian peer reviewed and gave feedback on all my work, and Evan helped me coding in Python to create all my graphs and do data analysis. So yeah, that's the end of my presentation. Thank you to everyone here that watched this.